Okay, let us start our last lecture for today. Actually, this lecture should have been read by my PhD student Kirill Nekludov, but I've got so impressed by the topic that I asked him to let me to deliver this lecture by myself. So Kirill will give a talk tomorrow, and we'll tell about our recent and quite surprising results on variance networks. But, well, this will be tomorrow. So the topic of today's lecture is stochastic MCMC techniques. And so probably the first question you should ask is why it's called stochastic. MCMC, these are already Monte Carlo methods. They're already stochastic by definition. So it sounds like some kind of tautology. But of course, the reason is because now we'll use the same tricks like we do in stochastic optimization in order to build up scalable MCMC methods. So remember that mostly MCMC estimation is used as a kind of Bayesian inference, especially for the cases when the true posterior distribution is intractable. If it's intractable, it's known up to normalization constant, and this is usually given by the product of prior distribution times the likelihood of our observed data or training sample. If we could normalize it, that would be true posterior distribution, but this is rarely the case, so only for the case of conjugate distributions, only for the most simple models. Otherwise, the distribution is intractable. And if it's intractable, we know it's only up to normalization constant, and there are several ways of how to deal with such models. One of them is variational inference. Another is Monte Carlo methods, mostly Markov chain Monte Carlo methods. So they allow to sample from a true posterior distribution even if it's known up to normalization constant. So even if we do not know normalization constant, we may still more or less efficiently generate samples from the true posterior distribution, and then we could use these samples in order to estimate the needed statistics, to compute expectations, to compute variances, confidence intervals, and so on. But up to now, we by any way need the access to the unnormalized true posterior distribution, and in this true posterior distribution, in numerator of Bayes equation, there's a product over all objects in our training set. So if we have, say, 100 of objects, this is not a problem. But if we have, say, 1 million of objects, that's a problem. Each iteration of an MCMC method becomes extremely expensive. So the question is whether it's possible to scale MCMC methods and to use some kind of mini-batching, just like we do in stochastic optimization. Until very recently, it was widely believed that it is not possible. Because if we omit some objects here, we definitely end up with a different posterior distribution. So it's not trivial how to come up with a mini-batched version of MCMC estimation. So probably this is why the better name for the talk would be mini-batch MCMC techniques. But the problem is that it now became a standard terminology, stochastic MCMC. This is why the lecture was called as stochastic MCMC rather than mini-batch MCMC. So first of all, let us briefly sum up what we have learned so far. So for complicated models, when the exact Bayesian inference is not tractable, we have to use one of several approximation techniques. And we have studied up to now Monte Carlo techniques and variational Bayes. So this table briefly summarizes its main advantages and drawbacks. So first of all, bias. By bias, I mean whether we're dealing with a true posterior distribution or with some biased approximation. So this is not Bayes, this is bias. So for the main advantage of MCMC is that we are dealing exactly with the true posterior distribution. And just like the previous speaker have shown you on the example of Ising model, we've seen there that if we deal with the true posterior distribution, the results are a bit different from the factorized variational approximation, from the mean field approximation. So qualitatively, the behavior is the same, but it's still different. And the reason is because the variational Bayesian inference is biased. So it deals with approximation, but not with the true posterior distribution. And this is the main drawback of variational Bayes, and at the same time, this is the main advantage of MCMC technique. And by the way, I should say that MCMC technique is so useful and was used in so many practical applications that it was included in the top 20 mathematical inventions of 20th century, by the way. And probably the first practical application where Metropolis-Hastings scheme was used was in Manhattan project in order to compute the parameters of an atomic bomb. So this is really very useful technique. Okay, so next, sampling and unsampling. So how to generate samples using MCMC using variational Bayes. So it appears that in variational Bayes everything is pretty simple because we have access to directly the density function. The density function Q of our variational approximation for the true posterior. Since we have access to directly the density function, we may quite easily generate samples from it. At the same time, MCMC techniques are known to be quite inefficient. Why so? Mostly due to two reasons. One reason is that if we're dealing with Markov chain Monte Carlo, we're building Markov chain, and we need some time to warm up this Markov chain until it converges to some stationary distribution. So we have to emit, say, 1,000 of first samples, because they're not samples from the true posterior distribution, because the Markov chain haven't converged yet. But even after it converged, formally speaking, we may now take each generated sample. But the problem is that neighboring samples are highly correlated due to the fact that they're generated by Markov chain, and each following sample is conditioned by the previous sample. So if we need to have a set of independent samples from the true posterior distribution, we need to subsample the objects we generate by MCMC, and thus making the procedure hundreds of times slower. So it's known that MCMC techniques are very slow in comparison with variational Bayes. So they're not biased, but they're slow. Next is the access to the density function. So for the variational inference, as I already mentioned, we have direct access to the density of our variational approximation. For the MCMC techniques, we don't have access to the density. We may only generate samples. And finally, the likelihood function. In both cases, we need to have access to the likelihood of the training sample, of the training set. And at the same time, there are some alternative approaches, which are called likelihood-free models, such as generative adversarial networks, when you do not need to have access to the likelihood function. And as you have probably noticed, there is one column in between MCMC and variational Bayes. It stands for IPM, or implicit probabilistic models. This is a very new technique, which from my personal point of view is extremely promising, and currently we still have just very primitive tools of working with implicit probabilistic models, but they're developing at the current moment. So probably in a year or in 2 years, we'll get much more tools for working with the implicit probabilistic models. And this will be the topic of tomorrow's first lecture, read by Dmitry who will describe what is this and how it can be positioned with respect to these two techniques. In some sense, we may say that implicit probabilistic models is some intermediate tool which takes the best of the two worlds, the best from MCMC and the best from variational Bayes. So this was a short advertisement for tomorrow's lecture, so please do not miss it. So now let us return to standard MCMC. The most popular technique is Metropolis-Hastings scheme. And in Metropolis-Hastings, we have some proposal distribution. This is Q, which allows us to generate new potential sample if we have a current sample theta prime. So we have theta prime, we condition on theta prime our proposal distribution Q, and we generate new candidate point theta. As this proposal distribution, well, we may use, for example, just Gaussian distribution with some variance centered at the point we are conditioning on. So centered at the point theta prime. So we have generated new point theta, and now we have a choice whether to accept theta or to keep the old point theta prime. To decide whether we should accept new point, we perform so-called Metropolis-Hastings correction. So we compute the following value, alpha, and this is the probability with which we accept a new point theta. So after we have computed alpha, we simply compare it with a sample from uniform distribution from 0 to 1, and if alpha appeared to be larger than u, then we accept new point theta. Otherwise, we just replicate the old point theta prime. And of course, if alpha became larger than 1, then we definitely accept the new point. So the physical sense is well, more or less clear. For simplicity, just imagine that this distribution is symmetric. For example, like I mentioned, like a Gaussian distribution where we with mean at the condition. So then this distribution is definitely symmetric. So we may just vanish the Q term, and then we have a relation over our posterior distribution computed at the new point and at the old point. So if a new point is more probable, if it has a larger probability density, then we will definitely accept the new point. But if the new point has less value of density function, then we may still accept it, but with some probability. So such scheme encourages us to concentrate in the areas where our posterior distribution is large. And this is exactly the areas we're interested in. Because we would like to generate the points mostly from the areas of high value of our posterior distribution, because we want to sample from posterior distribution. But sometimes we allow our scheme to generate the points from less probable regions. This is why this probability is always non-zero. But the main problem is that if we substitute in our posterior the expression from Bayes' theorem, we will end up with such expression. And here we have a likelihood for the training set, computed with respect to all objects in our training data. And if our training data is large enough, this scheme becomes extremely inefficient. Because on each iteration, we need to compute this alpha, and it will take us quite time. So what I'm going to tell you next is the paper published last year, an efficient mini-batch acceptance test for Metropolis-Hastings. And from my personal point of view, this can be regarded as a breakthrough in MCMC. Up to now, for about 8 years after the development of stochastic variational inference, it was widely believed that this is the only scalable technique for approximate Bayesian inference. So if we want to do Bayesian with the large data sets, this is our only choice, is to use stochastic variational inference, because this was the only scalable technique. And probably only the situation started changing only last year with the appearance of this paper. We showed that actually we may use MCMC in an extremely efficient, scalable manner by using mini-batches instead of computing likelihoods with respect to the whole data set. And so let us now see how it could happen. So first of all, let's review old known Barker lemma. So consider the logarithm of our acceptance probability. So this is our acceptance probability in Metropolis-Hastings scheme. We take logarithm and we denote it as delta. And Barker lemma states that if we find such function g of s, which satisfies the following condition, so x per s times g of minus x equals g of x. So this is not just one function, but there are many functions that satisfy this condition. So if we take arbitrary function that satisfies this condition, and if we start doing Metropolis-Hastings with the acceptance probability that is given by g of delta, so we take the classical acceptance probability, we take log, and then we compute function g of this log of acceptance probability and use the result as a new acceptance probability. If we do this, we'll still sample from the same distribution. So with this acceptance probability, we will still satisfy the detailed balance equation, and it can be proved that we will keep sampling from the same distribution as we would if we used this value as an acceptance probability. So by the way, why do we need this acceptance probability? Why do we need Metropolis-Hastings correction? Who can say? Right. Why at this point we need to compute this alpha and accept points with some probability? Why just not to accept any point generated by distribution Q, by our proposal distribution? It would be random work and so what? Okay. So first of all, if this distribution is such that the corresponding Markov chain is agordic, and this is almost always the case, we will generate samples from some stationary distributions after a while, after our Markov chain has converged to stationary mode. The problem is that these distributions will be different. It will not be the true posterior distribution. We'll generate samples from different distribution. And in order to avoid this, in order to ensure that we generate samples from the true posterior, we need to perform such kind of correction. Okay, so now what Bakker lemma states is that if in the Metropolis-Hastings correction we are using not this expression under logarithm, but g of log of old acceptance probability, and if we'll use it as a new acceptance probability, we'll still sample from the true posterior distribution, from the same distribution. You may ask, well, if we sample from the same distribution, then why should we do this? And of course the answer that if we are not going mad, we should not do that. Why? Because any application of such function g only reduces the acceptance probabilities in total. So our Metropolis-Hastings will become less and less efficient. And I try to illustrate it on this picture. So this is our delta, log of acceptance probability. In standard Metropolis-Hastings correction, what do we have? If our delta became larger than 0, or if we take exponent, if our alpha value became larger than 1, then we definitely accept the new point. So here's the acceptance probability is 1. If our alpha value is less than 1, or equivalently, if our log of alpha, delta, is less than 0, then we accept the new point, the point theta prime, the point theta with some probability, which is less than 1. But if we apply Barker's lemma, we end up with some kind of this function. So this is our new acceptance probability. And you see that it's strictly below the acceptance probability given by standard Metropolis-Hastings scheme. So in both cases, we will sample from the same distribution. But if we apply Barker lemma, less points will be accepted. So we'll spend much more time for generating sample of the same size. So seems computationally inefficient. And this is true. This is why nobody used this Barker lemma in practice until very recently. But as we already know what happened with the stochastic optimization, some techniques based on stochastic gradients, which were completely inefficient for the small data sets, surprisingly became extremely efficient in the cases of large data. So the same happens here. So again, if we apply g function to just our standard log of acceptance probability, we will ensure that we will still sample from the same distribution. So let us consider the following function g of s. So this is well-known logistic function. It satisfies the condition in Barker's lemma. So this means that if we compute our delta, log of acceptance probability, if we apply a function g, and if we compare the outcome with a sample from uniformly distributed random variable from 0 to 1, and we accept the new point with this probability and keep the old point with the remaining probability, we will still sample from the same posterior distribution as in standard Metropolis-Hastings scheme. Now let us compute g inverse from both parts. So you see that this function is definitely invertible. So then when we say that in order to ensure that we sample from the correct distribution, we need to compare function delta with x given by g inverse of u. And now the question to you. So let's consider function g. This is function whose value tends to 0 when argument tends to minus infinity, and whose value tends to 1 when s goes to plus infinity. So this is exactly the properties of cumulative density function, or CDF, of some random value, right? Good. So who can answer what happens if I take randomly distributed random variable from 0 to 1 and compute inverse CDF? I will get sample from a distribution whose CDF is given by the function g. And it's known that function g, if we consider it as a CDF, as a cumulative density function of some distribution, we actually know what is this distribution. So this is known as a logistic distribution. So this is a logistic function, or CDF. If we differentiate it with respect to x, we'll get the probability density function, and again, it can be computed in an analytic manner in closed form. So this means that instead of generating sample from 0 to 1 and substituting it to inverse CDF, I may simply generate sample from logistic distribution. And so I need to compare my value delta with a sample from logistic distribution. If my delta appeared to be larger, I accept the new sample. If my delta became lower, I keep the old sample in my Monte Carlo Markov chain. Okay, so this is it. You may also notice that this is symmetric distribution, and x log, so I will denote x log sample from logistic distribution. So x log is distributed, has the same distribution as minus x log. Okay, so now if we apply Barker's lemma in our Metropolis-Hastings scheme, we end up with the following procedure. First of all, we compute delta function. So this is log of our acceptance probability. And you see that it's given as a sum of log ratios of likelihoods on the objects from our training data, plus log ratio of our prior distribution times the values of proposal distribution. So this is just standard Metropolis-Hastings acceptance rate after taking logarithm. So now I need to compare this value of delta with a sample from a logistic distribution. Or equivalently, I should perform the following comparison. And this is the condition under which I accept the new point theta prime. So if this value is larger than 0, I take theta prime as my new sample from true posterior distribution. If this condition doesn't hold, I keeping the old value theta as a new sample from my posterior distribution. So this scheme is equivalent to Metropolis-Hastings. But what is good in this scheme? In this scheme, I have summation with respect to the objects in my training data. And each time I have summation, the first thought that should come to your mind is to consider whether it's possible to switch to mini batches of data. And well, it is really possible. So let's consider the following expression, delta star. So delta star is unbiased estimate for the true delta. But the only difference is that delta star is computed not using the whole training data set, but just a mini batch of data, a mini batch of B objects from my training data. So what can we say about delta star? According to central limit theorem, we may say that it has some normal distribution centered at the true value of delta. So delta star is delta plus x norm, where x norm is a normal distribution with zero mean and with some variance, and this variance can be computed using the statistics, using these equations. So just use the statistics of how large variance, how much is the variance of individual objects within the mini batch. So this value is computable. Well, to be strictly correct, this is not Gaussian distribution. It would be Gaussian distribution if the number of points in my mini batch would go to infinity. Since I'm dealing with finite sets of objects, this is not normal distribution, but it's pretty close to the normal distribution. So now let us assume for simplicity that this is normal distribution, and we'll prove a bit later that actually it doesn't matter. So this distribution differs only by a tiny portion from the true posterior distribution. Okay, so now we know that, so now we have access to delta star. And delta star is delta plus some normal noise. But what do we need? We would need to have access to delta plus logistic noise. And instead of it, we know how to compute delta plus normal noise with these variants. So, and now, wash the hands, like illusionists usually tell us. We know how to compute, we know the parameters of this logistic distribution. We know the parameters of this normal distribution. The idea is genius and simple. Let us add some additional random variable here in order to obtain this value. And we know the parameters of both xnorm and xlog. So the question is how to compute additional correction. So this is what we're going to do next. So let us express xlog as a sum of xnorm plus some correction. Some correction is also so this is correction distribution with some unknown density, density function. So we know the density function of sum. We know the density function of one of the items, but we do not know the density function of the second item. Are there any ideas of what can we do in this situation? Yes, so this is almost what we're going to do. So we have access to this expression. Formally speaking, this is not exactly normal distribution, but again, doesn't matter for now. So what we're going to do, we would like to decompose delta plus xlog as delta plus xnorm plus xcore. Or equivalently, this is delta star plus xcore. So if we find the parameters of how xcore is distributed, we'll be able to remove our delta with delta star. And we'll be able to perform Metropolis-Hastings correction even if we have access just to mini batch of data, even if we know how to compute just delta star instead of delta. And delta star can be computed thousands of times faster or tens of thousands of times faster than delta in the case when our training data set is huge. So this is how our scheme is going to work. I compute delta star using just a tiny mini batch of our data. Then I sample from this correction distribution. Please note that this correction distribution is dependent on the variance of our normal noise here. Because if normal noise has different variance, of course I should have different correction here. But this is obvious. So I sample from correction distribution and I accept new point theta star if this constraint holds true. Otherwise, I keep the old point theta. So now the question is, two questions. One of them is how to sample from correction distribution, how to find the parameters of this correction distribution. And the second is what is the error which was induced by the fact that we used normal distribution, although actually our noise here was not exactly normal distribution. It would be normal only when the number of items in Minibatch goes to infinity, according to central limit theorem. If we are working with the finite sums, they are not exactly normally distributed. So, okay, let us address each question. So first of all, again, consider the sum. We know the parameters of the first item, we know the parameters of the sum, and we would like to know, to get access to the parameters of our distribution of x-score. And actually this is pretty easy, well, more or less easy. So we're using the properties which we all know from the theory of probabilities. We know, for example, such property. CDF of sum of two random variables equals to the convolution of CDF of the first item convolved with the PDF of the second item. The proof is given here. So it's, well, just one line proof. This is cumulative density function of the sum of two random variables. By definition, it can be expressed as follows. And if we combine the terms here, we'll end up with this expression. So this is a convolution of a cumulative density function of y times probability density function of x. So now let us apply this and know that we know the CDF of x norm, the CDF of logistic distribution. So it's not difficult to find the PDF of a second item of this correction distribution. We cannot find it analytically, but we may easily approximate it by histogram using, well, some uniform grid. So this is how it can be done. So we simply minimize the difference between the result of convolution and the CDF of logistic distribution, plus some regularizer just to ensure that it will not diverge. So if we define if we denote the CDF as M, CDF of normal distribution as U, and CDF of logistic as V, CDF of normal distribution as M, and the the value you would like to estimate as u, we are getting just, well, standard regularized least squares problem whose solution is given in explicit form by this line. So by performing this equation, we're able to compute the histogram of a probability density function for the correction distribution. And using histogram, of course, I may now sample from this distribution. Note that the problem is not so difficult because everything is one-dimensional here. So we have one-dimensional random Gaussian noise, one-dimensional logistic noise, and one-dimensional correction distribution. So after we've done that, we're now able to sample from this correction distribution. There is just one more tiny issue which remained. Remember that I told that our correction distribution depends on the variance of a normal noise. So this is a delta star, true value of delta plus normal noise. But normal noise depends on the variance of our statistics computed within a mini-batch. So for different mini-batches, we'll have different values of sigma squared here. And if we have different values of variance, we should have different correction distributions here. So what should we do? Should we really compute the parameters of our correction distribution each time when we have each new sigma squared of delta star? Well, this is possible, but this is not computationally effective. And the much better idea is the following. Let us fix some sigma value, for example, sigma value equal to 1. And each time we take mini-batch whose sigma squared of delta star is less than 1, let us simply add additional Gaussian noise so that it would be Gaussian noise with a variance of 1. And if we have Gaussian noise with a variance of 1, added to our true and accessible value of delta, then we simply use correction distribution, which was pre-computed for sigma equal to 1. And what should we do if our sigma squared here became larger than 1? The answer is simple. Please increase the size of your mini-batch. The more and more mini-batch you are using, the less and less becomes this variance. So you keep increasing your mini-batch until this sigma squared becomes less than 1. After it became less than 1, you simply add some additional noise, Gaussian noise here in order to ensure that this Gaussian noise has variance of 1. And if you know that your Gaussian noise has a variance of 1, you simply add some correction distribution here, and you are done. So this value can be computed with 0 and can be used as an acceptance criterion for your Metropolis-Hastings scheme. And please note that in this scheme, you still all you need to have access to is the access to the mini-batch of your data. So probably. Okay, so now let's address the second question. Whether the difference between the normal approximation for our finite sum and the true distribution of our finite sum really matters or not. And the answer is actually not, because if we compare our approximation when we use normal noise here with the true answer, we may limit the difference in CDFs by this value, which is also computable, and we can, well, set some predefined threshold epsilon. And again, we may just keep increasing mini-batch until this statistic becomes less than epsilon. And if it became less than epsilon, we may ensure that the difference of this cumulative density function, the supremum of this difference, is less than epsilon. And if it's less than epsilon, then known result, by the way, obtained by a group by Max Welling, states us that if we have a difference in acceptance probabilities that is less than epsilon, that we may ensure that the stationary distribution to which we converge will also be different on some tiny value. So this means that we may, in some sense, ensure the approximate convergence of our scheme to the true posterior distribution, which is very nice. And so this is our final algorithm, known as stochastic Metropolis-Hastings. So we have proposal distribution, and if we are dealing with just d-dimensional real space, so you may use just isotropic Gaussian here, for example, centered at the old point theta. So we generate candidate point theta prime. Then we take mini-batch of data. We compute statistics over this mini-batch, statistics over sigma squared and this epsilon value, which is given by this equation. Again, everything here is computable, so don't worry. And we keep increasing mini-batch until we obtain two of these conditions. So first of all, our variance within the mini-batch should be less than 1. Second, our statistics should be less than some predefined threshold delta. This is needed to ensure that we will converge to the true posterior with the accuracy of delta. And then, after we have collected sufficient number of objects, we simply perform Metropolis-Hastings correction. We compare this value. So we have delta star. We have some additional noise, Gaussian noise here, in order to ensure that this value now will have a variance of 1. And then we add some correction distribution, which was computed exactly for the case when the variance of the previous term was 1. And so this correction distribution, its parameters can be pre-computed in advance before we start Metropolis-Hastings scheme. So all these operations are extremely efficient. And so we either accept the new point theta prime if this condition holds, or we keep old point theta. So now the question may arise whether, so probably the main bottleneck is here, increase mini-batch. Can't it happen that we'll have to increase mini-batch size until we reach the whole data set? And the reason is surprisingly, unfortunately for us, no. And here is the comparison from the last year's paper. So here's their results with the two analogs, two previous attempts of trying to build scalable Metropolis-Hastings scheme. In both previous attempts, again, the authors had to deal with the mini-batches over different size. And this is a result of Metropolis-Hastings sampling from 1 million of points from the mixture of Gaussians. And you see that in previous attempts, at least sometimes, you had to use the whole training data, the whole set of 1 million of objects. While in the scheme which I have described you now, the largest mini-batch contained of just 1,000 of objects, but the most of mini-batches were even smaller. So on no iteration, we had to use the whole training data. This is very nice, and this really opens new options for scaling Markov chain, Monte Carlo methods for the cases of large training data sets. So this was the first part of my talk. Now let's have a break, and then we'll review another technique, which is in some sense compatible with the previous one, and which is also relates to stochastic MCMC methods. Okay, so up to now, we have studied how we can scale up standard Metropolis-Hastings scheme. But as was taught on the previous lecture, there are more efficient MCMC techniques which rely not only on the value of a density function, or an unnormalized density function we would like to sample from, but also on the value of its gradient of log density. So up to now, in my talk, we have never used the gradient of log density. So we used only the values of density, again, up to normalization constant. So, and this density was given by the product of prior distribution times likelihood of the training data. We also used the unbiased estimates for the log likelihood of training by switching to mini batches. But again, we've never used the gradients. Although in many cases we can easily obtain those gradients. And the common sense probably should hint us that if we try to use gradients, we could end up with a much more efficient sampling schemes. Because each sampling scheme, roughly speaking, tries to identify the regions of high values of our density function and to sample from that. And if we have access to the gradient, then it's much easier to find these regions of high value of density. So one scheme, which Dmitry told you, was a Hamiltonian Monte Carlo. I will tell you about a bit different scheme known as Langevin Dynamics. Or actually, English-speaking speakers usually use Langevin, although it was a Frenchman, and the right word is Langevin, actually. But well, anyway. So this Langevin dynamics can be considered as a limit case of a Hamiltonian Monte Carlo, as a limit case of Hamiltonian Monte Carlo, and in some sense it's much more easier to understand what's happening. On each iteration, we're trying to update our current sample theta by adding delta theta t at each moment of time. So, and this theta update is given by this equation. So epsilon over 2 times gradient of our log density times some normal noise, but not just arbitrary noise, but normal noise with a zero mean and the variance given by epsilon, and epsilon is a step size here. So in some sense, we're making gradient updates, but gradients are noisified by the normal noise with some predefined magnitude, with some predefined variance. And it can be proven. We will not provide the proof here. It was proved by Langevin many decades ago that if we do this, we'll obtain a sequence of thetas, and these thetas will be distributed according to this distribution. And in our case, if we do Bayesian inference, and we would like to sample from posterior distribution, note that the gradient of log density of posterior distribution is equivalent to the gradient of log density of numerator in Bayes equation, because denominator doesn't depend on theta. So if we take the log and start differentiating with respect to theta, we'll end up with 0. So then it means that the gradient of log density is equivalent to the gradient of numerator, and this is the gradient of log prior times the gradient of log likelihood of the training data, plus normal noise, which is again normally distributed with a zero mean and variance of epsilon. And this update we also multiply by epsilon over 2. So if we perform these updates, we may ensure that we will sample from the true posterior distribution. And this process is known as Langevin dynamics. Please note two facts. First of all, this is correct procedure. So we may really sample from the true posterior. Second, we make use of the gradients of log density, and this makes the process much more efficient than just random walk with Metropolis-Hastings correction, which we considered in the first part. And finally, this is, in some sense, limit case of Hamiltonian Monte Carlo. Again, it can be shown. Or you may treat Hamiltonian Monte Carlo as some generalization of Langevin dynamics. So they do not contradict to each other. But now what's interesting here? Wow, here we have a gradient of log likelihood. And then we have gradient of log likelihood. Again, the first thought that we should come to your mind is, well, maybe we should try to switch to stochastic gradient, which we will compute according not to the whole data set, but just according to some tiny mini-batch of data. Okay, and this is exactly the content of the paper Bayesian learning with stochastic gradient Langevin dynamics. Again, by the way, written by Max Welling and Yiwi Te several years ago. So I will tell at the end why this technique, although known for several years, didn't become too popular, although it's widely known in the community, but it's relatively rarely used. I will explain you why. So the idea is pretty simple. Let us take the standard Langevin dynamics equations and let us remove true gradient with a stochastic gradient. So this is it. We take a mini batch of data, we rescale it in order to get unbiased estimate, and we try to use this equation for updating theta. Please note that there is one significant difference. Our step size, epsilon, is now time dependent. So here, here, and here. And this is pretty similar to what we have in when we switch from a gradient descent method to stochastic gradient descent. I think you'll probably, it should be told you on the lecture on stochastic optimization, but just to remind. It is known from optimization theory that if the function is differentiable and you are doing gradient descent, then you may update your arguments with a constant step size, and you are guaranteed to converge to local minimum. Why it happens so? Because the closer and closer you are to the minimum, the less and less are your gradients. So even with the constant size, your updates become smaller and smaller until you converge. At the same time, when you are using stochastic gradient descent, it is required that your step sizes should go to 0. Why? Because when you're using stochastic gradient, even at the point of local minimum, your stochastic gradient is not equal to 0. It's always, well, with the probability of 1, it is non-zero. And this means that if you're using constant step size, you will never converge. So in order to converge, you need to decrease your step size with each iteration. So the same, we're trying to do the same here. So our epsilon t's are step sizes which are decreasing with each moment of time, just as an analogy with the stochastic gradient descent. Okay, so this is the schema. Now we need to prove, or at least to provide some intuitive analysis, why it works. Why such scheme really allows us to sample from the true posterior distribution. Okay, let us try to get some intuition. So first of all, let's denote g of theta, the true gradient of our log density, the true gradient of our log posterior distribution. And ht of theta is the deviation, is the difference between our stochastic estimate and the true gradient. So we take our stochastic gradient, we subtract the true gradient, and we obtain that this deviation, ht of theta, is approximately normally distributed with a 0 mean and some variance Vt of theta. The variance itself is even doesn't matter, and we'll now understand why. So again, just like in stochastic gradient descent, we'll use the following epsilons. So the epsilons themselves should sum up to infinity, and the epsilon squared should be less than infinity. Who knows why? Why these are the most popular requirements for the step sizes in stochastic optimization and in this stochastic Langevin dynamics? Right, but the question was why in stochastic gradient descent we need the same conditions here. The reason is intuitively quite simple. The first requirement ensures that we may take arbitrary initial condition and we may go arbitrarily far from it. If it didn't hold true, it might happen that we simply could not find the optimum point because it was located too far from our initial point. By ensuring this condition, we may guarantee that even if it's quite far away, we will still converge sooner or later to this point. And the second condition ensures that our step size goes to 0 at infinity. So this is, of course, rough intuition, but it's still better than nothing. Okay, if these two conditions hold, then we may split our sequence of epsilons to such parts that for each part, the sum of epsilons equals to the same constant epsilon 0, which is, by definition, would be less than 1. Let us do that. It is always possible. So we may fix arbitrary value of epsilon 0, and we may always split our sequence of epsilon t's on such intervals that the sum of epsilon t's within the interval equals, well, at least approximately equals to epsilon 0. Okay, if we do this, let us now consider our stochastic gradient Langevin dynamics updates. So this is one update. So we take epsilon t over 2. We take the stochastic gradient, and stochastic gradient is given by the true gradient plus some normal noise, plus another normal noise, which comes from Langevin dynamics. And this normal noise has a variance of epsilon t. Now let us make several stochastic Langevin updates. This number of updates. So, and remember that the sum of epsilon t's, for t going from ts plus 1 till ts plus 1 in the index, yields exactly to epsilon 0 by definition of our subsequence. So let us make such number of updates. So this is just summation. Now please watch. Please note that if we sum these normal noises, eta t's, for different t's, this is equivalent to adding just one normal noise with such variance. Because we know that the sum of two normal variables is a normal variable with a variance provided by the sum of our initial variances. Okay, this is just stochastic gradients. Now let us add and subtract to each item the true value of gradient at the point theta ts. So this is the true gradient. And now let us remove this gradient outside of our summation. If we do this, and we'll sum just these epsilon t's, we'll end up with the epsilon 0 over 2 times the true value of gradient at the point theta ts. Why do we do this? The motivation is pretty clear. We would like to obtain the update of standard Langevin dynamics plus some random noise from this equation, in order to compare the true update and the update we are doing in stochastic scheme. So this is exactly what we're doing. So we take this out of the summation, and these epsilons then sum up to epsilon 0. This is again, this epsilon sum up to epsilon 0. And so this guy plus this guy outside of summation gives us exactly the updates of standard Langevin dynamics scheme. And all the remaining parts are just, well, some noises. So, and all we remain to do is to prove that these additional noises have much less order of magnitude. So these two items is just standard update of Langevin dynamics. And these guys have a much less order of magnitude. So in particular, the last term is some random noise with zero mean, and it has order of O of epsilon 0. And this guy, it doesn't have zero mean, so this is systematic error. But it has the order of O over epsilon 0 squared. And at the same time, this noise, which comes from Langevin dynamics, has the order over epsilon of the order of O over squared root of epsilon 0. So if epsilon 0 is a tiny variable, is a tiny value, then this noise dominates the remaining two. And this means that up to negligible noise, which can be ignored, which can be simply ignored, really several updates of our stochastic gradient Langevin dynamics, of our stochastic scheme, correspond to one update of two Langevin dynamics. And this is well, pretty nice. So this means that we can really perform our Langevin dynamics updates using only mini batches of data at each iteration. So these are the proofs. I will skip it. Those who want to study it, well, may use it afterwards. So, yeah, right. So this is what we have proven. So several updates of our stochastic scheme are equivalent to just, well, are equivalent up to negligible random noise, are equivalent to just one update of two Langevin dynamics. But at each iteration, we used only mini batches of data. So, seems perfect. The problem is that why nobody widely uses these techniques? And the answer is pretty simple and quite discouraging from the first glance. Actually, by doing such scheme, we still imply some errors. We still need to perform Metropolis-Hastings correction. Otherwise, our stationary distribution will tend to diverge from the true posterior distribution. So what was taught by the authors of this stochastic gradient Langevin dynamics paper, they told, okay, we do not know how to perform Metropolis-Hastings correction without computing the statistics through the whole data set. And this is computationally very expensive. So if we need to perform such kind of Metropolis-Hastings correction, there's no need of developing efficient sampling schemes, because after each sampling iteration, you will need to perform Metropolis-Hastings correction. So the authors thought, okay, we don't know how to do that. Let us just use very tiny values of epsilon 0. And if the values of epsilon 0 here are tiny, then we may just ignore Metropolis-Hastings correction. Approximately each sample will be accepted. This is true to some extent. But the problem is that if you are using tiny values of epsilon 0 here, this means that your Langevin dynamics became very, very, very slow. So it samples from the correct distribution, but its samples, the neighboring samples, are extremely highly correlated, because you're moving just like a turtle, very slowly. And such scheme becomes impractical, especially when we're sampling in high-dimensional spaces. But now we know the answer. So this paper was written several years before stochastic Metropolis-Hastings appeared. So now we know how to perform Metropolis-Hastings correction using just tiny mini-batches of data. This means that we may take the best of the two worlds. So we may use the knowledge about gradients of our log density, or the stochastic gradients about our log density, and the exploitation of this knowledge allows us to perform much more efficient sampling. And at the same time, we know how to perform Metropolis-Hastings correction, which allows us to use larger step sizes here without the risk of converging to the wrong distribution. So we may take the both of the two worlds and obtain stochastic gradient Langevin dynamics with a large step size and with stochastic Metropolis-Hastings correction. By the way, nobody did it, because stochastic Metropolis-Hastings appeared just several months ago, so probably the man who will incorporate the stochastic Metropolis-Hastings correction to the stochastic gradient Langevin dynamics will get paper at NIPS or at iClear accepted without any doubts. So my claim is that the combination of these two techniques will lead to the breakthrough in scalable Markov chain Monte Carlo methods. And they will again become extremely popular, and at least as popular as stochastic variational inference techniques, and will give us a new tool, new scalable tool for processing the data, for dealing with complicated posterior distributions without implying any kind of bias in our process. So with working with the true posterior distributions rather than with some, generally speaking, quite rough approximations for the true posteriors. So this is really nice, and I hope that during this lecture again you've got some feeling of the spirit of scalability, or what should you do to make the known technique scalable and applicable to the large training data. So probably at this point I would like to conclude. So just some remarks. So these stochastic MCMC methods provide us new tools, the sampling techniques of a new generation. You should also realize that the problem of sampling from some distribution, which is known up to normalization constant, is not trivial. So this is a hard problem, but this is extremely important problem, because in many cases you need to collect some statistics from the posterior distribution, although you do not have access to it. Well, you have, but up to normalization constant. So it's not easy to sample from arbitrary distribution, although it may simple from the first glance. No, it's not. And this is why the Markov chain Monte Carlo methods have been developed. Now we know how to scale them up. So now we know how to apply them for the Bayesian models when we have a large observed data, large training data sets. Of course, this stochastic Metropolis-Hastings correction, due to the application of Barker's lemma, will lead to larger rejection rates or smaller acceptance rates. But even if the acceptance rate becomes, say, 10 times less than in standard Metropolis-Hastings, but if each iteration requires, say, 10,000 of times less time, so it's 10,000 of times faster than the true Metropolis-Hastings, then we're still doing 1,000 of times faster than the conventional Metropolis-Hastings techniques. So it is worth sacrificing the acceptance rate at each iteration at the expense of making each iteration orders of magnitude faster than the initial scheme. So these are the main conclusions, and I hope that you will get some understanding of why it's important. So this is the end of my talk, and I'm ready to answer questions. Yep.
Thank you for a really, really nice talk in introduction into the scalable MCMC methods. I will have a few questions and comments. First of all, a very small comment of that. In both of the approaches, we require that the likelihood factorizes easily, which is not the case for even like multivariate Gaussian, right? With some non-independent covariance metric structure, right? Which means that we have a really, really limited amount of applications of those techniques. And the second one, I mean, why don't we just use an auxiliary state Monte Carlo and introduce some latent variables zi's that switch on and off a particular observation and then sample from the joint space of those z's and the original parameters. And if there were some studies on that, and if those approaches seem to work well for those cases when the likelihood factorizes.
Well, there are, of course, some studies on that as well. They simply go beyond the scope of the summer school. I'm unaware, I'm not aware of any scalable versions which use mini-batching for the case of auxiliary variables, although I do believe that such scalable techniques are also possible. Probably the only reason is that nobody did it before, but probably someone will do it in the nearest future.
Thank you. I have a question about the first part. So before this trick for stochastic MCMC was invented, so one could naively do standard MCMC with a mini-batch, and this would be wrong mathematically, but how wrong would this be in practice? Because like variation bias is also not entirely unbiased?
Good question. Unfortunately, it's not easy. It's not trivial to answer because you may always construct such examples where, even if you use just mini batches with the wrong Metropolis-Hastings correction, but you may still sample from the true distribution if you construct the distribution by a specific way. For example, if all objects are the same. So then you will have no deviation. In general case, I don't know.
Could you comment graphs on the previous slide?
What?
The graphs.
The graphs?
Yeah.
Yep. So do you want me to comment them?
Yeah.
Okay. This is. I was too lazy and decided to skip it. Okay, these are the graphs from the Wellington paper on stochastic gradient Langevin dynamics, and they analyzed the impact of different noises. So here we have three types. Probably. Okay. Here we have two types of noise: the green one and the red one. And they use this graph to ensure that the red noises, which are for different rounds, are shown here. After some iteration, becomes much less, orders of less than the Langevin noise. So approximately from this point, when the Langevin noise starts dominating the noises implied by the stochastic estimation of gradients, we may say that this stochastic gradient Langevin dynamics becomes equivalent to Langevin dynamics. And on the right graph, it was shown the rejection rate. So if we do true Metropolis-Hastings correction, so we see that the larger is epsilon 0, well, the more rejections we should actually have. But if we use very tiny epsilon zeros, our rejection rate becomes, well, approximately 100 or even one object per 1,000. And then you may simply ignore this Metropolis-Hastings correction. But the price to pay is that you are now moving like turtle.
Thanks for an interesting lecture. I want to ask following question. What big X and Y on the 21st slide means? Thanks.
What big X what on 21st slide?
X and Y on 21st slide.
Oh my God. What is 21st slide? This is 21st slide.
Where U stack is calculated. when we are trying to sample from correction distribution. Yeah, the next slide.
Apps. This?
Previously shown. Previously.
This?
Not. Yes, this slide.
And what was the question? What is phi sigma c sigma?
What big X and Y means.
XI, YJ. Yes, these are just nodes in our uniform grid. Because we need to minimize the difference between the result of convolution and the true CDF. We can't do it in on a real line. We discretize. We establish some kind of grid on this real line, and we try to minimize the sum of differences with respect to the nodes of the grid. So XI and YJ are simply the nodes on this grid. And the grid was uniform from -20 to +20.
So a bit of a technical question, I guess. The algorithm to the first part, the stochastic MCMC, we had this second part increase the mini-batch until like these two conditions, right? And do we actually have to make it for every theta prime? And do we ever decrease the mini-batch? So is it unique for theta prime, or is it just pre-computed and then left?
Well, you usually start with some relatively small size of mini-batch, and in each iteration, say from 10 objects in your mini-batch, or 50 objects. And at each iteration, you see whether these two conditions hold true or not. So the sigma squared and the epsilon, whether there is less than delta or not. If the conditions hold true, you simply keep this mini-batch. If the conditions do not, you increase mini-batch. But at next iteration, you again start with a small mini-batch. Okay? So if there are no questions, or
could you please provide a bit more intuition on how sort of the Lagrange stuff is a limit case of the Hamiltonian method?
I'm afraid I'm not ready to provide it right now. Sorry. I could say that Langevin Dynamics correspond to just one step of leapfrog integration, but I'm afraid this will not tell you anything. So in Hamiltonian Monte Carlo, you need to perform several leapfrog steps in your variable times momentum space. But in Langevin Dynamics, you may show that you simply need to perform one leapfrog state, and then you may eliminate these additional variables. And you may substitute them directly to the update of theta, and you will get this Langevin dynamics equation. So, okay, if there are no questions, thanks for the attention, and we're waiting for you tomorrow.